Hello, guys. You're welcome to this lecture. In this lecture, I want to cover the exponential functions. So just as we did for the logs, I'm going to start with the general exponential functions, and then we'll look at laws of exponents. Some of these you've seen before. We'll look at derivatives of exponential functions, and then we'll move on to a special case called the natural exponential functions. We'll look at the number e as a limit, right? The number e, which we'll talk about, can be written as a limit. And then we end with the derivative of the natural exponential functions, okay? That is the plan for this lecture. So the exponential function is a function that is of this form. Some number raised to the power x, right? And the number a has to be greater than 0, and it's some constant. So it could be 2, 5, 7, 9, whatever. It's a number, right? Raised to some variable x. So that is the definition, like, of the exponential function. So this is a graph, right? Just chose a to be 2 here. If you plot a graph of the exponential function, you're going to get this kind of shape, okay? So it starts from here and then increases and increases exponentially. So if you've had the term exponential increase, right, this is what it's referred to, right? So all the way from negative x here, all the way back there, increases at x equals 0, it is 1. You can see that from here, 2 raised to the power 0, right? Any number to the power 0, well, apart from 0 is 1, right? So at 0 is 1, and then it keeps increasing and increasing. So get familiar with the shape of exponential functions, all right? This is just an example of that. If the x here was negative, you'll have the reverse. Well, note this is, so before we go here, note that this means that you see as x goes to infinity, as x becomes bigger and bigger, this whole number becomes bigger and bigger, right? It becomes larger and larger. That is why this guy is increasing exponentially going to infinity. Okay. On the other hand, if you're going backwards, right? If x is from here, if x is becoming negative, of course, this guy is decreasing and decreasing very fast. See that? Let me see if I can pull out my pen here. I'm not sure. And then I can try to illustrate something on the okay. So here, so you see that when x is negative, you're going to have y is 2 to some negative number, right? A negative number. So let's call it, well, let's say -5. But 2 to the -5 is the same as 1 over 2 raised to the power 5, right? And now that is very small. That is 1 over like 32, right? And then imagine that the 5 was even bigger as you go here. Then this is bigger and the number becomes even smaller. Okay, so as you go to negative infinity, you expect that the graph will decrease. Okay, so as x is becoming negative, more negative is decreasing, and x is becoming positive is increasing. So if you like the limit as x goes to infinity of 2 to the x or e to the x, for instance, this guy should be going to infinity. You see, and as x the limit as x goes to negative infinity, if you're going this way, then you expect this guy to go to 0, right? It gets closer and closer to 0. Okay. So that is the graph of the exponential function. So get familiar with how the exponential functions look. Okay. This is just an example of that. Now, so if x was negative, right? If I have 2 to the negative x, the graph is going to be this black curve here, right? It's going to be this. Okay, that's because as x is becoming negative, this quantity here becomes positive. See that? I have 2 to the negative x. So if x is negative, then the quantity is positive. So this has become bigger, positive y's that are getting bigger as I'm going towards negative infinity. And as I'm going towards positive infinity, as x is increasing, right, this guy becomes smaller, right? Because this is the same as 1 over, right? This is 1 over 2 to the x. This is the same as 1 over, this is the same as 1 over 2 raised to the power x. I don't know where this is coming from. Let me do this. Okay, so y is 1 over 2 to the x. So as x is becoming greater and greater, this is becoming a bigger number. 1 over a big number is very small. So x is going this way. This is becoming small. That is why it's decreasing in this direction. So for x negative, you have 2 to the negative x. This is how the graph of the exponential function looks like. Okay. Now, not just 2, this could have been any number, right? It is a to the x, as long as it's not 0, right? As long as it's positive. So if you use 4, for instance, in this case, 4 raised to the power negative x is same as 1 over 4 to the x, the graph is going to look like that. Okay. So be familiar with the graphs of exponential functions. They're either increasing this way or they are decreasing, depending on the sign of x here. Okay. Depend on x. Good. So let's move on. This is, let me get rid of these guys. Well, I can leave them and then move on to get rid of the comments. Okay, good. So we have looked at the graph of the exponential functions. The next thing we want to look at is some laws, right, of exponents that you probably have seen some of these before. If a and b are some positive numbers and some x and y are real numbers, then a raised to the power x plus y is the same as a to the x multiplied by a to the y, okay? And then these are the ones. We'll prove the first 3, and then you can try to prove D and E, okay? So we'll do them for this general case. Then when we get to natural exponential functions, the same apply. You only replace the A with E as we did for logs, okay? So let's prove this first one. This says that if I have a to the x multiplied by a to the y is the same as a, just sum the exponents here, you get x plus y. You can take the log of both sides. Actually, we are starting from here. Okay, we're going to take the log. If we take the log of this, all right, remember that for a product, you have to be, it becomes an addition, right? So log of a to the x multiplied by a to the y is the log of a to the x plus log of a to the y, okay? So this is equal to, note this, from the properties of logarithms, log to the base a to the x is just x, right? It's just x log of a, which is 1. So this is just x, and this guy is just y, all right? And so this will be equal to log, well, you can also write this, right, as log to the base a, multiply base a, and then a raised to the power x plus y. You see? Because I can go from here back here using the definition of the logarithm, right? So this x plus y can actually be written at this. Good. The log function is 1 to 1. You saw that, right? If it's the we don't have the log here, but we looked at the log, right? If you remember the log function, the ln, for instance, is basically just increasing like this. So if you like use the horizontal line test to test, and you see that it's actually a 1-to-1 function. Because it's 1-to-1, if log to the base a of this expression here is equal to log to the base a of this expression, then the expressions in bracket here must be equal, okay? So this guy here has to be equal to this. Because remember the definition of a 1-to-1 function, we said a function is 1-to-1 if f of x at 1 is equal to f x2, then x1 has to be equal to x2 as the definition of log. So if this guy is equal to this and log a is 1-to-1, then the argument must be the same. So that is why we get that. So using this, we've proved the first one. We can also prove the second one, a to the x all to the y is a raised to the power the product x times y. Okay, so we're going to let r be equal to what is in bracket here. Let r be equal to a to the x and take the log of this. We're going to take the log of this. So log to the base a of a raised to the power x y, that is basically this guy. We call this r, right? So this is log to the base a, ry is equal to, well, from the properties of log, I can bring y here, have log to the base a of r, okay? So basically this guy now this guy is equal to that, right? But remember that r here is a to the x, okay? So we have this. And this, of course, will be equal to xy log, right, is a to the x, so I can bring the x down here. So I have xy log to the base a, and that is equal to, and again, using the properties of logs, I can take all of this and put it up here on a, right? So this is log to the base a raised to the power xy, okay? So like we did for the previous one, that means that this guy here, log to the base a of this, is equal to that. Okay, so since the log once again is 1-to-1 function, the argument of the log must be the same. So this guy here has to be the same as a to the power xy, and that is what you get here. Okay, so that is the proof for the second one. To prove the third one, C, which is this, to prove this, okay, we're going to use a relation that we've seen before. Okay, so we're going to prove this one. To prove it, we want to establish this, right? Well, we already know this from our study of logarithms. We know log to the base a of xy is the sum, right? Log ax plus log ay. So we're going to use this. You can look it up in the notes on logarithms. So we have this already, so apply it. Okay, so to prove this expression here, we're going to take the right-hand side here and show that it's equal to the left-hand side. Log to the base a of this guy is a product. It's a to the x multiplied by b to the x. So I can split this into log of a to the x plus log of b to the x, right? Now, this is to the power x, so I can bring the x down here. I can bring this x down here, and that gives me this. I can factorize the x, pull it out, and you have log a of a plus log b of log a of b, right? Good. Note that this now is a sum which I can turn into a product, right? Using the properties of logs. So this is x log of a times b, okay? Note that, again, with the properties of log, I can take this x up here. And so finally, I'm going to have this guy here to be equal to log of a times b all raised to the power x. Again, the logs will cancel out if you like, because log is 1-to-1. Therefore, a to the xy, a to the x, b to the x has to be equal to ab all raised to the power x. So if you have this product, what this says is that you can basically multiply the a and b, and then, oh, this guy here. Oh, yeah. Right. Basically multiply this and raise all of this to the power x. Okay. Good. So we've proved that first three. You could try the other ones if you want to. Okay. We are going to move on now to derivative of exponential functions. How do you differentiate exponential functions? Okay. Before we come to the natural exponential function. So you can do that by using first. There is an alternative way, but first you can do that using the definition of the derivative, right? If you have a function, you don't know how to differentiate it. Well, you can always rely on the definition. So we know that the derivative of a function f of x is equal to this, right? You've seen this in calculus 1. But our function in this case is a to the x. So wherever I see x in this case, I replace it with x plus h. So I get a to the x plus h minus the function is a to the x. So I have that all over h. Okay. So f prime is basically, well, there is some algebra going on here, right? This is the same as a to the x multiplied by a to the h, right? A to the x is here, a to the x is here, so you can pull it out. That is why I have a to the x here. And I have limit as h goes to 0 of this guy, okay? You can pull it out because this has no h in it, so the limit doesn't affect it. All right, good. Now take note that f prime at 0, right, will be equal to this. A is greater than 0, so x a raised to the power 0 will be 1. This is 1 here. So if I put 0 there, all I have left is the limit expression. Okay, so f prime at 0 is this. Therefore, f prime at x will just be equal to a to the x multiplied by f prime at 0. All right, there's a reason we are doing this, okay? We'll come back to it. This will help us to find the derivative of this. Remember that all we are doing is that we want something, an expression for the derivative of a to the x, this exponential, okay? This is going to help us to achieve that using the definition of the derivative. Okay, good. Now, recall, right, that in our study of log, we said that ln y, for instance, is the limit as x goes to 0 of this expression. And we said you could replace this y here is some number. You can replace it with a or h or some number. If you do that, you're going to get these expressions, right? Ln a is this. It's equal to this. X can be replaced with some h, and you get that, right? So basically, ln a can be written as limit as h goes to 0 of this. Okay, good. But if you go back, remember, f prime at 0 is this, right? And we just showed that this guy is actually ln of a, okay? We've just shown that ln a is that expression there, which implies that f prime at 0 is ln a. F prime at 0, which is this expression here, is ln a. So once again, if you go back, instead of f prime at 0, which is this guy is ln a, so you can replace this with ln a. So using the definition of the derivative, you have shown that the derivative of the exponential function, right, f prime of x, of d dx of this, right, f is a to the x, is equal to a to the x ln a. Okay, that is this. This guy is ln a multiplied by a to the x, ln a times a to the x. Okay, so that is using the definition of the derivative, you can show that d dx of the exponential function here is given by this expression a to the x multiplied by ln a. Basically, you keep the same expression, the same exponential expression, and multiply by the ln of the base, right, of a. Here's an alternative. Instead of using the definition of the derivative, you could also use this approach, okay, which is much shorter, right? So f of x is this. We can also write this expression here, right, as e to the ln of a to the x. Remember that we said that the e and the ln, right, appear to cancel each other out. When they do, you get back this, right? So you can write this expression as e to the ln a to the x. You can, using the properties of log, you can bring the x down here. That gives you e to the x ln a, okay? So instead of differentiating this guy, which we don't know how to do, we know how to differentiate this. We know how to differentiate e to some, some variable. So we'll use that approach. So f prime of x will just be equal to the derivative of this. Basically, you leave this and differentiate the exponent, right? If you differentiate x ln a, you're just going to get ln a. So you leave this and then differentiate x ln a. If you do that, just get ln a, which is this. Okay, so f prime of x will just be equal to, remember this guy here, this guy, if you go back, is actually a to the x, right? Okay, so this guy here is a to the x ln a, which is the same expression that we got before. So the derivative of a to the x is a to the x multiplied by ln a using this simpler but a bit trickier approach. Okay, you have to remember that this can be written as this, and then the rest becomes easier. Okay, good. So that is how you differentiate logs. Here is a more general way of doing it. In this case, this u here is a function of x, okay? The ones we looked at, it's just a to the x, right? Now, this is some function of x. So u here could be like x squared plus 1 or x cubed minus x or something, okay? So this theorem says if you have d dx of something like that, a to the u, where u is a function of x, this can be written as ln a to the u multiplied by du dx, okay? Okay, we can prove that here. Again, a is positive and a is not equal to 1. U is a differential function of x. I've mentioned that. So to prove it, you can let y be equal to a raised to the power u. Okay, y is a to the u, and then you can apply the chain rule. So dy dx would basically be d dx of this guy. Using the chain rule, right? Because there's a u here. You're going to have d du of a to the u, then du dx. Okay, but this, we know how to differentiate this, right? From our previous thing that we did. To differentiate, if u was x, for instance, right? We're just going to have a to the x multiplied by ln a, right? So this will just be a to the u ln a. So we know how to, this is the first thing that we show, this guy. No, here, this is ddx of this. You see, in this case, we are having the x there is a u, and the variable here is u as well. So we can apply this. So you just be a to the u ln a. Okay. So we know how to do this part, this bit. Okay. So that is just a to the u ln a multiplied by du dx. And this is what we want to prove. Okay. So if you have this general case, this is how you do it. d dx of a to the u is a to the u on a du dx. Okay, good. So we are done with the derivative of exponential functions. We'll look at the natural exponential function and then the number e, right? E as a limit. Then once we are done with that, we'll look at derivative of the natural exponential functions. Okay, so here the natural exponential function is just a special case. In this case, instead of a to the x, you replace the a with e, right? We'll look at what e, the number e is. But you replace a with the number e, and then you get what is called the natural exponential function, just like we did for the natural logs, right? And it's represented by exponential x or e to the x. Okay, sometimes written like this, sometimes like that. And then it satisfies this, that the ln of e to the x, remember ln is log to the base e, right? Okay, so ln of e to the x is just x. And again, it satisfies this relation that e to the ln x, once again, we said the ln and the e appear to cancel, right? E to the ln x is just x. So the natural log is the is this expression that satisfies these relations, okay? Also, if you have e to the x is equal to y, using our study of logarithms, we can take the log of both sides, if you like, of just from the definition of the of log. This is also equivalent to ln y equals x, right? Again, ln is log to the base e. So log to the base e of y is x, means that e raised to the power x is y. Okay, and it is the inverse of the natural logarithm. Okay, we actually show this, right, using the cancellation equations when we're doing our logarithms. Okay, and you can see that in the graph here. When we're doing logarithms, we saw ln, right? Ln x is this, and this point here is 1, right? Okay, so this is the graph of ln x. And we've also seen the graph of exponential functions, which are, this is 1 here, they cut 1 here, and then, they increase exponentially. Okay, this guy is a reflection using the reflective properties of inverse functions. You see that this guy here is a reflection of this about the line y equals x. Okay, so the natural exponential function and the natural logarithm function are inverse functions, okay? And you can also prove it using the cancellation equations. Okay, good. Here's another definition, right, that you can use for the, there's a third one that will show that you can use for the number e, right? So we're looking at the number e here. It is a number such that the ln of e is equal to the integral of 1 to e of the function 1 over t, okay, the t. Now, so you define e such that this integral here is equal to 1, okay? Remember that we already defined the ln x to be this, right? Ln x can be defined by this. So basically replace x with e and you get that, right? So e is defined as this, ln e is equals this, and we want e to be such that when I integrate from 1 to that e, I should get a 1, all right? In other words, if I integrate from 1 to some number, which we are calling e, the area under the graph of this must be exactly equal to 1. And that e is approximately equal to this number here, okay? So that is, if you like, the definition of what the number e actually is. When you see the natural exponential, this is what it actually means, okay? Good. Here, okay, here's a theorem. We're not going to prove it. It's easy. You can look at the previous stuff. Ln e to the x, again, ln and e cancels and you have x. All right, for all x. Note that if you plug in 1 for x here is a number from negative infinity to infinity, so you can use any number. If I put 1 here, I'm going to have ln e to be equal to 1. So the natural log of e is actually 1, right? Log to the base e of e is 1. As we said, log to the base e of a is also 1. So this is not surprising. And e to the ln x is just equal to x, okay? Good. We can use these ideas to solve these problems. These are some examples. You want to solve ln of x plus 3 is equal to 6. Well, ln is log, right? So this means that x plus 3 is equal to e raised to the power 6. So x plus 3, we can actually compute this to get approximately equal to this, so that our x will be equal to, take this minus 3, you get this guy. If you wanted the a number, right? Otherwise, you could just take 3 here and you have x is e to the 6 minus 3, and that will be your exact, right? Exact solution. We can solve this as well. If you like to get x, right? You want to solve for x. So take the ln of both sides, right? If you do, remember that ln to the ln e of this will just be equal to the power, right? So you have 1 minus 2x is equal to ln 5. Take 2x then bring this there. So 2x is 1 minus ln 5, divide through by 2. Well, I haven't done that here. I computed this. I got the approximate value of this, right? 1 minus ln of 5 is actually this guy. And then you have 1 minus it is this. So divide by true now, and x is approximately equal to this. If you don't want the approximate value or a number, right, you could basically just divide by 2 and then you get x. Okay, good. Depends on what you're solving for. The number e, like we did for the logarithms, can also be written as a limit. So we want to look at in the next couple of minutes, look at the number e as a limit. So if you let the function f of x be ln x, we can use the definition of the derivative to compute the derivative of f of x, right? Okay. So, and then from there, it will help us to find e as a limit, okay? So once again, we know that from definition, f prime is given by this, right? But f now is ln, so I'm going to have ln of x plus h minus ln x all over h, right? If I plug in x equals 1, okay? If I put x is equal to 1, why am I doing that? Remember that we said that it's not from here. Let's see. If I put 1 in here, right? Oh, we want to pull out the e, right? If you put 1, you're going to have ln of 1 here minus ln of 1 plus h, I should say. Remember, ln of 1 is 0, so this will go to 0. So I'm going to have f prime at 1 will be equal to this guy, okay? Because ln of 1 is 0. So you have this. Good. You can rewrite this as that. Okay. Good. Now this is a ln is log, right? So I can take this fraction 1 over h here and take it up here from the properties of log. So I'm going to have this. Okay. So f prime at 1 is actually equal to this. Okay. Good. But remember f of x is ln x, and we know how to find the derivative of this. The derivative of ln x is just 1 over x, right? So you have 1 over x, that is, which implies that f prime at 1 has to be equal to 1. And so I can equate this guy to be equal to 1, right? Because this is f prime at 1, that is f prime at 1. So ln of this is equal to 1, okay? Good. Now, since ln is a continuous function, we can actually interchange the limit and ln. I can take the limit inside the ln, right? When I do, I'm going to have ln of the limit as h goes to 0 of this guy is equal to 1, okay? Good. So you have ln of something is equal to 1. Remember, ln again is log to the base e. So this means e raised to the power 1 is equal to this expression here, right? So the expression here, the limit here is actually equal to e raised to the power 1, which is just e. So this is another definition, if you like, of the number e. So the number e can actually be represented by a limit, right? The limit as h goes to 0 of this guy, 1 plus h raised to the power 1 over h. This h could be any number here, right? This, I could replace h with x. So you have x here, you have x, you have 1 over x, right? It could be y. So don't get confused with the variables. So this could be, once the variables are consistent, this is a definition for the number e. Okay, good. So that is another way you can represent the number e. Note that you can get a similar expression for e to the x, right, as a limit if you just substitute x equals 1. But if you don't do this substitution, you can actually prove this. Okay, if you let now, let n be 1 over h. So here, we want to turn this into a different limit. Instead of h going through 0, we want to turn it to a limit that is going to infinity. So make a substitution for 1 over h and see what you get. If you do that, of course, as h goes to 0, n must go to infinity, right? So n goes to infinity as h goes to 0. And so wherever we see h, we can replace with n, right? Or 1 over n. And so we're going to have a limit as n goes to infinity here, right? This is 1. H here is now 1 over n, and then 1 over h is just n, okay? So that's what we have here. So you have 1 over n, and this is just n. And that is also a definition of e. So this is just a previous equation, but now with a different limit. Now n is going to infinity. Well, you can also once again replace this n with any variable as long as you're consistent with it, right? You can use n to be x, and then it is still e. So that is how you represent the number e as a limit. Okay, that is so you can use the proof, right, that we just did to also show this, guys. You can try to prove these. Okay, good. Okay, so just like we did for the laws of exponents for the general case, you also have these laws for the natural exponents. All right, they follow the same pattern. The difference is that we used a, right, in the previous one. Now is e. That's the difference. So e to the x, e to the y is just e to the x plus y. This can be written as that. If you have e to the x r, you can do it at e to the, you can multiply the x and r and get that. So if you want to prove, you can try your hands on them and take a look at the general cases. They follow a similar pattern, so you can look at that. Good. Let's finish off the video, which is a bit longer now, and do the derivative of the natural exponential functions. Okay, this is not going to take very long. I have about 2 slides to go. So if u is a differentiable function of x, right? U is a function of x. D dx e to the x is just e to the x. If I differentiate the natural exponential function, I just get it back. But now in this case, this u here is a function of x. So again, this could be like x squared or x squared plus 1 or something. It's a function of x. If you want to differentiate that, first pull out your e to the u, and then differentiate the exponent, differentiate the u dx, and that gives you this. Okay, so I have the proofs in my lecture notes, or you can follow a similar thing as the natural logarithms. Okay, great. And that brings me to the end of this lecture. You can try these exercises on the exponential stuff. You can try to simplify these expressions, okay, using exponential and log. You can solve these equations for x, okay? And then you can show that the given functions are inverses of each other. Basically, you want to use the cancellation equations, right? Yes, right? Where you find a composition of the functions. So find the composition of these functions, f of g and then g of f. If you get x, right? For both of them, for both cases, then you have shown that they are inverses of each other. So you can try that. And then you can find the derivatives of these functions, okay? Using all the machinery that we just learned. And you can also find the limit of these guys, okay? We know how the exponential function behaves, right? So you can try to use that idea to find these limits. Okay, good. So I'll end this lecture, this video here. And then I'll come back later and continue with probably the integration, and then the integration as well as inequalities of logarithms, okay, logarithmic inequalities. So we'll look at that, and then integration of these logs and exponents. Good, okay.